Okay, let's look at some relationships involving the heat of reaction. So, this change in enthalpy is for a specific chemical reaction. If the reaction changes, then delta H has to change also. So sometimes we manipulate our chemical equations, and these are the rules for if you do this to the equation, what do you do to delta H? So if a chemical equation is multiplied by some factor, then delta H is also multiplied by the same factor. When we balanced redox reactions using the half reaction method, we took those individual half reactions and multiplied them by a factor to end up with equal numbers of electrons, right? So that's the sort of thing you might have to do. So if this equation, this reaction, A plus 2B makes C, has a delta H here, delta H1. If I multiply this equation by 2, I'm talking about reacting twice as much stuff, and so the change in enthalpy is going to be twice as large. If I reverse the chemical reaction, write it backwards, make the products into the reactants, then delta H changes sign. So if A plus 2B going to C is delta H1, let's say that's positive. I had to put heat into it to make that happen. And now I'm going to look at the reaction the other way, going backwards, C going to A plus 2B. If in the first one I put heat in, the second one I have to take it back out, right? It's just opposite. So for this reaction, it's just opposite in sign from the first one. Reverse the reaction, change the sign. And then Hess's law makes use of the fact that these things are state functions, and the process by which you get there is not important. It's just the difference between the final and initial. So Hess's law says that if the chemical equation can be expressed as the sum of a series of steps, then delta H reaction for the overall reaction is the sum of the heats of reaction for each step. So we can draw a diagram like this where we have A plus 2B going to C, and that's a positive enthalpy here. And then when C reacts to form 2D, it releases a bunch of energy. But what we're interested in is going from A plus 2B to 2D. So we can write the first reaction, delta H1, the second reaction, this is delta H2. If I add these two reactions together, as the C's cancel out, and I get this guy down here, the change in energy, the enthalpy change for this one is the sum of those two. I added the two reactions. To get the change, I add the two delta H's. So this is a weird set of stairs, or climbing something, I don't know. I just made it up right now. Up to this first ledge is 2 feet, and up to the second ledge, maybe this is some sort of a cat tree or something, I don't know. Up to here, from here to here is 5 feet, and here to here is 3 feet. What's the difference between the very top and the very bottom? 10 feet? How did you figure that out? You just added these, right? So from the top of this platform to the bottom is 10 feet. It's 10 feet whether, if you're going down, whether you go down on the ledges and do it in 3 steps, or whether you do it in one big leap. The distance is the same, right? That's the idea over here. Each of these chemical reactions is a step with its own energy, and the overall change is the sum of those steps. But some of them are positive and some of them might be negative. What this allows is for us to determine delta H for a reaction without actually having to do the reaction. There are some reactions where measuring delta H in the lab might be difficult. But if we know delta H for reactions that we can add up to get what we want, we don't actually have to do the reaction. So what we do is we manipulate reactions with known delta H's so that we get the reactants of interest on the left, the products of interest on the right, and we get the other species to cancel out. And then we add those up, we add the delta H's, and we get the change in H for the whole thing. So consider the following chemical equation. 2A plus B forming C. And for this reaction, as written, the delta H is 122 joules. So this is asking, what's delta H for the reaction 2C to make 4A plus 2B? What is different about this reaction compared to that one? It's multiplied by 2. So I need to multiply delta H by 2. What else is different? It's backwards, right? So it's backwards, and so I need to multiply by -1. That doesn't look right. That's subtracting 1. Oh, it's minus 244. So it must be this one down here. Any questions? Find delta H for this reaction. N2O plus NO2 making 3NO. And this is what we have available. We've got these 3 reactions with known delta H's. We want to find delta H for this reaction. What we need to do is combine these equations in a way that they add up to this one. So some of you will find this very fun. It's a puzzle. It's like a logic puzzle. There's lots of different approaches where you come up with the same correct answer. What I like to do is I like to start with this first reactant. So I want N2O as a reactant. I'm going to look through what I've got here and see which of these is N2O. So I'm looking for N2O. Which reaction has it? Just the bottom one, right? It's here. So I want that as a reactant. Here it's written as a reactant, so I'm going to write that one down as is. 2 N2O gas, giving me 2 N2 gas plus O2 gas. And I didn't do anything to the equation, so delta H is the same. So I've got that as a reactant. I also want NO2 to be a reactant. Which one of these equations has NO2 in it? The first one, right? Here's NO2, but it's in the product side. So I need to reverse this reaction. So I'm going to write that one backwards. 2 NO2 making 2 NO plus O2. What do I have to do to delta H then? Change the sign. So it was negative 113.1, now it's positive 113.1. It's like buying and selling. It's the same amount, it's just opposite. And then my last thing that I'm looking for in the product side, I want NO. Well, NO is showing up in a couple of places. It's here, or there, and it's also in this one in the middle. So I could look at, I mean, it's possible, they're not going to, but it's possible that you have more stuff here than you actually need and you don't have to use all three. That's not going to happen. I've got both of my reactants and my product on the right side, but I've got extra stuff. I've got nitrogen and oxygen, and that's not in this reaction. So I need this other reaction, this middle one here, to get rid of the N2 and the O2. So here I've got N2 and O2 and some more O2 that I want to get rid of. And I can use this guy to get rid of those. There, now I've colored everything and nothing makes any sense. So I've got N2 and O2 on the product side and I want to get rid of them, so I want them on the reactant side. And that's going to make 2NO gas. So there's those guys. Did I do anything to delta H? I mean, did I do anything to the equation? To this one? Did I change it in any way? I just copied it down. So I'm just going to copy down delta H. 182.6. Now, as I go through to add this up, I've got 2 nitrogens over here and 1 nitrogen over here. Are those going to cancel? No. I need to multiply this bottom equation by 2. So 2 of those and 2 of these and 4 of those. And then I have to multiply delta H by 2 also. And now 2 N2s on each side, those are going to go away. I've got 2 oxygens here, and I have oxygen and oxygen, 2 oxygens there, so those are going to cancel out. Add the rest together, and I get 2 N2O gas plus 2 NO2 gas, making 6 NO. And delta H will be the sum of those, negative 163.2 plus 113.1 plus 2 times 182.6. Does this equation match with this one? Kinda and yet not, right? What's different about it? It's multiplied by 2. So I need to take this whole thing and divide by 2. 2 N2O divided by 2 becomes 1 N2O. 2 NO2 divided by 2 becomes 1 NO2. 6NO divided by 2 becomes 3NO. You okay with that? And then what do I have to do to delta H? The same thing, divided by 2. So delta H here is going to be 315.1, I don't know what that is, kilojoules divided by 2. $157.55, keeping the correct number of significant figures, 157.6 kilojoules. Any questions? I guess with that funky structure, that cat tower or whatever that was that I made, it was 10 feet tall, right? What if you were trying to measure how tall it was and you only had a 6-foot tape measure? You throw up your hands and say, I can't do it? No, you measure each step and you add them together, right? So that's what we're doing here, is we're finding individual steps that we can add together to get the whole thing, because we can't or don't want to measure the whole thing directly. Any questions? $157.6. Here's another one, because I think we need more practice. For more practice, 7.9. So we need to find delta H for this reaction, and we're supposed to use these two. So what should I do? What do we want to do with this first equation? Now I'm gonna label all these things with the highlighter, just to help us see them. So I need the yellow ones on the left side and the blue ones on the left side and the orange ones on the right side. And what about these that aren't highlighted? I want those to go away. But I'm going to start out by just taking care of the things I need to have, and then I'll see what I have to do with the other things. So this first reaction has my reactants and products in the correct place, so I'm going to write it down as written. So there's a desired product. Here's a desired reactant. It's a good idea to keep track of the delta H's as you go along. I didn't do anything to the equation, so I don't do anything to delta H. I just copy it down. The second equation has O3, ozone, as a product, but I need it to be a reactant. So I need to reverse this one, write it backwards. So 2O3 making 3O2. How do I change delta H? I just need to change the sign. All I did was write it backwards. When I write it backwards, I change the sign. So I've got oxygen as a reactant and oxygen as a product, and I don't want any oxygen in my final reaction. Are they going to cancel out as it is? No. I've got 3 oxygens down here and only 1 up there. So I need to multiply the top equation by 3. So multiplying by 3, I get 6 and 3 and 6, and this is also multiplied by 3. Now if I add these together, my oxygens will cancel out. So I get 6H2 plus 2O3, making 6H2O, and delta H is the sum of these things, negative 483.6 times 3 plus negative 285.4 minus 1736.2 kilojoules. My reaction down here looks a lot like what I was trying to get. Is it exactly the same? No. Up here I had 3 hydrogens, down here I have 6. Here I had 1 ozone, here I have 2. 3 waters, 6 waters. This equation is 2 times too large. So divide by 2. Divide this by 2, I get 3. I divide this by 2, I get 1, 3, and this is also divided by 2. So my negative 1736.2 divided by 2. Delta H is minus 868.1. Any questions? I promise you there will be a question like this in the exam. And it'll probably be one of the show your work problems, so I can give you partial credit. But then it's also worth more points.